Week 2, Lesson 1, Columns and Buckling. Machine design so far asked whether a part is strong enough. A column asks a different question. Is it stable? A long, slender column can fold sideways while the stress is still nowhere near yield. Today we build the language of that failure. Slenderness ratio, radius of gyration, effective length, and the end condition factor, K. Next lesson, those turn into Euler's buckling load. Here's the problem. A steel column, rectangular cross-section 50 by 100 millimeters, 1.5 meters tall, fixed at the base and free at the top. Find the area and the smallest moment of inertia, the governing radius of gyration, and the effective slenderness ratio. Notice there's no load. You don't need one. Slenderness is geometry and end conditions only. The buckling load is next lesson. Today, we classify. Concept 1. Buckling is a stability failure, not a strength failure. Stand a slender ruler on end and press. Nothing. Then at a critical load, it suddenly bows sideways. It never crushed. The stress was still below yield. Stocky columns fail by yielding. Slender columns fail by buckling, well under yield. The slenderness ratio is what decides which of those two governs. Concept 2. Slenderness ratio and radius of gyration. Slenderness is length over radius of gyration. Bigger means longer and thinner, more prone to buckling. The radius of gyration is the square root of the moment of inertia over the area. It folds the section's stiffness into one length. And the key move, a column buckles about its weak axis, the one with the smallest moment of inertia. So you always use the smallest radius of gyration. Concept 3. Effective length and the K factor. End supports don't change the real length, but they change how much of it participates in buckling. Effective length is K times L, and what actually classifies the column is the effective slenderness, KL over R. Pinned is the reference at 1. Fixing both ends braces it and drops K to 1/2. Freeing the top, a cantilever, doubles it to 2, and always take R about the weak axis. Concept 3. Continued. The K table. Pinned is 1. Both ends fixed, 1/2 theoretical, 0.65 recommended. 1 end fixed and 1 pinned, 0.7. Fixed free cantilever, 2, and just over 2 for design. The theoretical column assumes ideal joints. The recommended column bumps them up because real fixed ends are never perfectly rigid. Use whichever the problem specifies. Setup. 3 moves before any math. 1. Recognize it's a column, a compression member that can buckle, so slenderness governs, not just load over area. 2. Find the weak axis, the one with the smallest moment of inertia, and therefore the smallest radius of gyration. 3. Read the end condition and pull K from the table. Fixed free gives 2. Then build the table. Givens on top, a blank, and its formula for the area, the minimum moment of inertia, the radius of gyration, and the effective slenderness. Solve. Part 1. Section properties. Area is width times depth. The weak axis moment of inertia uses the small side cubed, HB cubed over 12. Then the radius of gyration is the square root of that inertia over the area. Quick check. For a rectangle, it also equals the small side over root 12. Same answer. The strong axis would give a bigger radius, which confirms the weak axis governs. Part 2. Effective slenderness and classify. Effective length is K times L. Divide by the radius of gyration and you get the effective slenderness. Now look what K did. Skip it and you'd get half the value and badly misjudge the column. At this slenderness, it's a long, slender column. It buckles elastically, well below yield. The exact cutoff and the buckling load are Euler's job. Next lesson. Final answers. Area 5,000 square millimeters, weak axis inertia about 1 million square millimeters squared. Radius of gyration about 14.5 millimeters. And effective slenderness about 208. A long column, buckling governs. All of it rode on 2 choices made before any arithmetic. Buckle about the weak axis and apply the fixed free K of 2. Traps. 3 quiet ways a column goes wrong. 1. Using L instead of KL. The length is the unbraced length. The column buckles over KL. so apply K first. A fixed free column is twice as slender as its height suggests. 2. The wrong axis. A column buckles about the weak axis, the smallest moment of inertia and smallest radius of gyration. Use the minimum, never the strong axis. 3. Theoretical versus recommended K. They differ, so read the exact value the problem wants and don't mix the two columns of the table. Quick recall. Slenderness is length over radius of gyration. Radius of gyration is the square root of inertia over area. Effective length is K times L, and effective slenderness, KL over R, is what classifies the column. For a rectangle, the weak axis uses the small side cubed. Golden rule: buckle about the weak axis and apply K before you divide by R. Next up, Lesson 2, Long Columns and Euler's Formula. Today we classified the column. Next, we load it. Euler gives the critical buckling load, pi squared times E times I, all divided by K times L squared, and the buckling stress with it. Every piece you built today, K, the length, and the weak axis inertia, plugs straight in. Before then, redo this column as pinned, and watch the end condition alone move the slenderness. Everything's at pprepengine.com. Cheat sheet, work solution, and a quiz attached here.